I'll come to the fifth and last lecture of week 12 of this course, and in this lecture I will give a short summary of what we learnt during this week and then do a few practice questions. Okay. Now, the practice questions in this topic will basically be related to the interpretation of the band structure. Okay. And so these will be pictorial questions. So week 12 lecture 5 will be summary of week 12 and practice problems. Okay. So what did we learn in week 12? So we first learnt about crystal momentum, then we learnt about the electronic configuration of crystals, how to fill electrons into bands in crystals. Then we learnt the very interesting and important concept of the density of states. Okay. And we saw how the density of states has the advantage that you do not have to pick a direction in the band structure. You have to pick a certain direction in which the wave vector is changed, but when you are looking at the density of states, you do not have to do any such thing. Then we saw how the band structure is related to the electronic properties of crystal, and finally we saw how the band structure is related to the optical properties of crystals. So now let us look at a few practice questions. Now the first question I am saying is classify the following band structures into conductors, insulators and semiconductors. Okay. So I have given all these band structures, and this axis is energy minus the Fermi energy, or actually truly it should be the Fermi level, okay, because we are looking at a finite temperature. Okay. So this EF actually refers to the Fermi level. Okay. So Fermi level and Fermi energy are the same at T equal to 0, but at finite temperature the Fermi level is used, and notice that the Fermi level can be where there is no band also. It can be in between bands. Okay. So E minus EF, and so this minus 5 electron volts. Okay. So this is 5 electron volts below the Fermi energy, this is 5 electron volts above the Fermi level, and similarly in these cases. Okay. So I have given an axis. Okay. I have said that this is plus 5 and this is minus 5. Okay. Again that means it is E minus EF is plus 5, that means it is 5 electron volts above the Fermi level, and this is 5 electron volts below the Fermi level. Okay. So classify the structures into conductors. Now here we see that the Fermi level is passing through one band. Okay. So clearly the first one should be a conductor. Okay. Now these two, okay, now here we see that the band gap is just of the order of order 1 electron volt. Okay. So this is clearly a semiconductor. Okay. Here the band gap is almost of the order of about, if you just estimate it, it looks like about 7 electron volts, and this would be an insulator. Okay. So what is important is you need to know the, if you want to know whether material is a semiconductor, conductor or insulator, you really have to have this scale, you really have to have this energy scale on the axis. Okay. And you have to know where the Fermi energy is. Okay. So you need scale of energy and Fermi level. Okay. So suppose I had just given you any of these without telling you where the Fermi level is, then you would not be able to tell whether it is a conductor, semiconductor or an insulator. Okay. Now let us look at the next question. So, this question is a theoretical question. It says that consider the following density of states. What additional information is need to deduce whether this material is a semiconductor, conductor or insulator? Okay. And this goes back to what we said last in the last question. So, you need EF, okay, that is the Fermi level. Okay. So, if EF is somewhere here, then you immediately know that it is going to be a conductor. So, if it is either in one of these regions, then it would be a conductor. Okay. Now, what if EF is in between these two? Okay, then it can be either a conductor or an insulator. So, 1, 2. So, case 1, okay, it is a conductor. Okay, let us take case 3, which is somewhere here in the middle of this. Okay, similarly, for case 3 is also a conductor. Case 2, okay, can be insulator or semiconductor or semiconductor. Okay, whether it is insulator or semiconductor depends on the band gap. So, it depends on band gap. Okay, so, the additional information you need to know is you need to know how much this band gap is. Okay, you need to know a scale of energy here. So, this energy needs to have a scale. So, you need to know this band gap, okay, and to know that you need a scale of energy on this axis. Okay, so, if you just have a density of states, you can't immediately say, I mean, the density of states has to have a proper scale, and you have to say where the Fermi level is. Only then you can tell whether the material is a conductor, a semiconductor or an insulator. So, again I want to emphasize that you know understanding things like density of states, I mean these are regularly shown in various literature to explain properties of metals, semiconductors and insulators. And so it is important that you understand the basics of the density of states, and then you can go to you can use it for more advanced materials. So, in these two problems we have seen how to understand whether a material is a conductor, insulator or semiconductor by looking at either the band structure or the density of states. Okay. Let me emphasize that band structure just shows one direction in K. Okay. So, it just shows one of the directions in K. Okay. It is possible that along some other directions the bands might actually go higher in K. Okay, but we are assuming that at least we don't have dramatic differences in the other directions. Okay, and so usually it is the band structure plus the density of states that really helps us decide on the properties. Now, one more question. So, here you are shown a few materials and you are asked to say which will make a good light emitting diode, and I should draw the Fermi level for the others. So, these are the Fermi levels. Okay, the green is the Fermi level. So, clearly in the first case, okay, you have a conductor. Okay, so obviously if you want a light emitting diode, it has to be a semiconductor. Okay, so you cannot have a light emitting diode. The second case, okay, now in the second case you have to identify what the band gap is. So, if you look at the structure, okay, then what you see is that the bottom of the conduction band is actually here and the top of the valence band is here, okay, and what you have is an indirect band gap. Indirect band gap. Okay, this is just based on this band structure, whereas in this case you have these two the bottom of the conduction band and the top of the top of the valence band are aligned, and this is a direct band gap. Okay. So, it is this that will make a good I do not want to say blue light emitting diode, I meant it will just make a good light emitting diode. Now, whether it is blue or not, okay, whether it is blue depends on the color needs information about Eg. So, what is the value of the band gap? So, for blue LED we saw that you typically need about 3 electron volts. Okay. So, if Eg is of the order of 3 electron volts, then we will get a good blue light emitting diode. Okay. Now, but in any case, this is the material that will make a good light emitting diode. Whether it is blue or not depends on the exact value of the band gap. So, these are the kind of ways in which you can analyze the band structure and the density of states. Okay. And with this I will conclude this lecture, and we will come to the end of lecture 12, and with that we have also come to the end of this course on solid state chemistry. And it's been 12 weeks, and I know there are a lot of things that we covered during this course, and some of them were I would say fairly intense mathematically, like the topics of symmetry and band theory. Okay. So, but overall what I have tried to do in this course is to give you a very general feel of some of the important concepts relating to solid state chemistry, and what you can do with this basic knowledge. Okay, you can delve deeper into topics of your interest. So, if you are interested in certain kind of materials for certain kind of properties, then this basic background should help you carry out whatever study you want to do in those materials. Okay. And I hope you have enjoyed taking this course as much as I have enjoyed teaching it. Okay. And with this I will conclude this course. Thank you.